All right, so we're going to go through the problems that I assigned to you guys based on the monster truck and the falling monkey in this video. And so let's just kind of jump right onto it. Now I realize this question seemed like it was really long, the first one, and in some ways these are kind of reversed of each other because the first question is quite a bit shorter than the second question. Get the hat on straight. But there's a lot more text in here, and I was trying to guide you a lot through this, and then I was trying to take the training wheels away for problem 2 to kind of let you work a little bit more on your own with it. So let's go through this really fast. So the monster truck problem says, as part of your co-op, your boss sends you to work at Monster Jam, a live motorsport event featuring monster trucks. You are tasked with doing calculations to ensure Gravedigger's finale is a success and nobody gets hurt, pictured below. Gravedigger is to jump a gap, a width of W, driving off horizontally. The edge of the other side of the gap is a height H below the edge that Gravedigger begins on. Note the approximation we're making is listed in the question H. This is excellent practice for what it's really like to be an engineer. I look forward to seeing what you have to come up with. I'll talk about that a little bit later. So the first thing we need to do is to define a coordinate system for this problem, drawing the x and y axis, defining an origin and the direction you are choosing to be the positive for x and y. And I won't read that part anymore, but it's a very important point. So I'm going to choose my origin to be right here, so that this is going to be the plus x and this is going to be the plus y. Now, why I say it's really important to do this is because all of the equations that you write later are going to be based off of this coordinate system. And so you need to make sure that you establish a coordinate system so that when you're writing your equations, there's some basis of comparison for the equations. Okay, so there's our coordinate system. The next thing that we want to do is we want to begin with the kinematic equations for acceleration, write the set of kinematic equations beginning with acceleration and working down to position that describe the situation according to your coordinate system and the given variables. Call it Gravedigger's initial velocity, v0, and the magnitude of the acceleration due to gravity, g. And I had a couple more comments there, but we'll just kind of hop straight into it. So there's two ways that you can really represent this. One is in terms of a table. The other is in terms of your vectors. And ultimately, these are going to be the same thing, and I'm going to show you exactly why. So for your x equations, you're going to have some acceleration for x, some velocity in x, some position in x that I'm going to call r sub x. In y, you're going to have the same thing. So a sub y of t is equal to something, v sub y of t is equal to something, and r sub y of t is equal to something. Okay, so let's just kind of go down the list. So starting with our acceleration in x, there's no wind, there's no air resistance. That means there's no acceleration in x. For our velocity in x, we're told that this has some initial velocity v0. So going back to our original kinematic equation, so I'm just going to write these right here real quickly. Oop, that's supposed to be an A0, not a Q. Oops. Control Z. Who lets this guy use a computer? He doesn't know what he's doing, and he's writing the same thing again. Okay, so this is A0. V of t is going to be equal to V0t plus A0. R of t, or x of t, is going to be equal to x0 plus V0. I made a mistake here. That's like that, and then this is like this. So this is like this, and then this is like this. Okay. So you can always, what I did there actually really quickly was actually applying dimensional analysis. I looked at the units and I realized that they were wrong for that that equation, and I was looking to compare the equations line to line to make sure that they were consistent. So there are checks that I'm doing in my head that you don't always hear me talking about, but when I'm describing the tools that you're using, checking equal signs, checking dimensional analysis, these are things that I'm kind of doing automatically. And if I do make a mistake like that, if I miswrite something, I'm looking back at it to make sure that it's consistent with the way it's supposed to be. Okay, so these are our general kinematic equations, so general kinematic equations. And so really what we're doing is we're looking at the situation that we have with the coordinate system, and we're writing in term by term what we have for each one of these, okay? So starting with the acceleration in x, I'm saying it's 0 because there's no wind, there's no air resistance. Nothing's causing acceleration in x. Velocity in x. Well, the velocity in x is just this given v0, okay? So that's this v0. Again, no acceleration in x, no term for it. R of x. So now, or r sub x of t. Now, this one has to do with our coordinate system because where we're defining 0 here with this coordinate system right here is telling us something about what x0 is. And that's to say that it's 0, okay? So all we're going to have in this equation is just the v0t, okay? Now let's look in y. In y, we have an acceleration due to gravity that's going to be pointing down. Because I chose my coordinate system to be such that up is positive for y, that says this is going to be minus g. And as a convention, the way I treat g, or the acceleration due to gravity, is always such that g is a magnitude. I put in the sign by hand, okay? You don't have to do it like that. There are always multiple ways to go about these. But this is a consistent convention that I use. And I think it's, honestly, I could go into more detail as to why, but I think this is the best convention to use. Okay, next equation. This one is going to be minus gt. And we can ask ourselves, well, is there an acceleration, or sorry, is there initial velocity in y? And there's not, because this is just going horizontal, okay? So no initial velocity in y, just minus gt. Position is a function of y. Minus 1/2 gt squared plus anything, well, based on the coordinate system we drew, no. Because at time t is equal to 0, Gravedigger's position in y is 0. So that's actually everything that we have, okay? So this is our table form of the equations. But we could equivalently write this in terms of vectors, okay? So I'm going to take what I have right here, and I'm going to move it so that I can write my vector equations. I was actually just going to move this down here. I'm going to write my vector equations directly across from where I'm writing my table. Okay, so you see I have these two lines here. Well, each line corresponds to a vector equation. So if I want to write this in terms of vectors, so let's underline these guys real nice so that they stand out. If I wanted to write these in terms of vectors, what this says is a vector as a function of time is going to be equal to 0 x hat minus g y hat. Similarly for velocity, if velocity as a function of time is going to be equal to v0 x hat minus gt y hat. And then r vector as a function of time is going to be equal to, this is going to be v0t x hat minus 1/2 gt squared y hat, okay? Now, a couple of things to note here if you want to write these in terms of vectors. So the nice thing about writing in terms of vectors is that you're encapsulating all of the same information that we have over here. So there's, over here on the left, we have one equation, two equations, three equations, 4, 5, 6. We have all that same information over here. 1, 2, 3. Oops, let's write this so it's in the same order. 2, 3, 4, 5, 6. All of the information is still here. But what we're doing, in effect, is we're able to really write all of that information. Instead of 6 different equations, we have 3 equations that carry all of the information that the table has. Now, there's a catch. And the catch is, if you're going to write this in terms of vectors, you need to be very careful with the way that you're using notation. So, see, every one of these equations, I have a vector, right? A vector is equal to something else that's a vector. So I have unit vectors. So v vector, unit vectors, R vector, unit vectors. Okay, I've seen more preventable mistakes on exams than I'd care to see that come from students trying to use vector notation and not expressing vectors as vectors. This ultimately is coming back to what I talk about a lot, which is making sure equal signs work out. So check equal signs. You'll see that if you say a scalar is equal to a vector, or you say like something like a vector as a function of time is equal to 0 minus g, well, then you could simplify this even. You could say that this is equal to just minus g. This is wrong, because what you're doing is you're saying that the things that are happening in x are affecting what's happening in y. Okay, you have to be very careful not to do that, because happens in x stays in x, happens in y stays in y, happens in Vegas stays in Vegas, right? So, not paid or sponsored, but if there's some folks from the Las Vegas tourist division, they'd like to toss me some money, I wouldn't be opposed to it. Okay, so make sure if you use vector notation, everything has to work out left to right on the equal signs. Vectors are equal to vectors. That's the big takeaway here. Okay, so these are the equations that we're going to need. We need to come back up and check what we're doing next. Use your equation to determine symbolically how long Gravedigger is in the air before it lands. Call this T land. Express T land symbolically in terms of known constants and box it. Okay, so there's two ways that you can kind of go about this. We know that a Gravedigger, ideally, what's going to happen is it's going to get over to this edge right here. And as it's undergoing that motion, it's going to fall a certain height, h. So I don't have this, this isn't drawn exactly the right way. This is more like that, okay? So I'm drawing it from like the bottom of the tires, okay? This has to do with the approximation we're making. We're always, with these kinds of problems, we're saying that the object of interest is a point. We don't care about the dimensions of the object itself. We treat it like a point. Okay, so we know that if it's going to make it over here, it's going to fall some height h, okay? So that's a good place to start. We say that our vector as a function of time is equal to t, what do I call this, t fall, just to make sure that I'm, t land, the time it takes to land, okay? This is going to be some distance in the horizontal direction. We'll call that d. We don't know what that d is yet. It might be w, it might be larger than w, it might be smaller than w. We don't know yet, okay? And this is going to be x hat plus h y hat. So now I'm saying it's falling that height h, but then when it falls that height h, is the distance going to be far enough to get it to the edge is the goal here, okay? So next part here, and this is, let me label the problems here. So this is A and B. So this is part A, and this is part B, okay? So this is going to be equal to the position vector function here, evaluated t land. Okay, so this is going to say v0 t land x hat minus 1/2 g t land squared times y hat. Okay. Now we can, what the vector is telling us is really, we can decompose this back into two equations. And so this says that d is equal to v0 t land, and h is going to be equal to h, or in this case it's actually minus h. There's a minus sign here because this is below, right? This is plus y, this is plus y, and then this is below, so it's minus h, okay? Again, things that look for consistency here. I saw this a little bit early because I saw that I would ultimately have a complex number when I took the square root. So for this, from the second equation here, I'm going to solve for t land. That says that t land is going to be equal to the square root of 2gh, okay? And then the horizontal distance it covers, which is going to be the next part that we're interested in, Yes. So for part C, we're going to find the horizontal distance that it goes when it's gone this distance vertically. And so for part C, and I'm going to box my answer here because I always follow my own directions. Put a box around our answer, and then we have C. So then what we can do is we can take this equation, plug it into that equation, and then this says that D is going to be equal to V0 times the square root of 2GH. Okay. Now we can check the units here. I'm going to leave that as an exercise for you guys because this is correct, but it's always good to check these things. And I gave you a bunch of checks to do here to make sure that you're not making mistakes. So the next part that we have is part C. This is part C, and then part D. C. I have these mislabeled, but it's not a big deal. Oh, A was the coordinate system. A is the coordinate system. So let's make sure that we're calling things what they're supposed to be. So this is A. This is B. This is C. This is C. And then this is D. Okay. I know what it is that I'm trying to solve for. I just wasn't sure how I ordered things. Okay. So now what we do in part E is we say, okay, well, let's throw some values to this and say, is Gravedigger going to make it or not? So the values that I give you are, you say 10 meters per second. Actually, E is asking, why is it okay to approximate this as 10 meters per second instead of 9.81 meters per second? The reason why it's okay to do that is because 10 meters per second squared is greater than 9.8 meters per second squared. And so if you imagine how far you're going to fall if the acceleration is 10 meters per second squared, it's larger than it is if it's 9.8 meters per second squared for the same amount of time. So if what you were doing in trying to see if this was safe or not is overestimate how fast, what the acceleration is. If you overestimate it, you're fine because you're building in some amount of wiggle room with your calculation. As opposed to if I underestimated, if I choose 9 instead of 10 meters per second here, then 10 meters per second squared, then I'm underestimating how far I'm going to go, and then that's when you run into problems. So just good tools for being an engineer, especially if you're a civil engineer, if you're trying to build in some safety factors into your calculations, overestimate how heavy something is or how fast something moves when you're doing a calculation, because then you're kind of building in this wiggle room for yourself. Okay, so that's that part. Now, the next part is actually evaluating this using, I have to see what values I chose. This was 10 meters per second, 10 meters per second squared. Velocity V0 is 10 meters per second. W, I believe, was 7.5 meters, and H is equal to 2 meters. And we're also saying that G is equal to 10 meters per second squared. Let me just check this real fast to make sure that I have this correct. Yep, we're good. Okay, so now let's calculate what D is. And then we're going to ask ourselves, is D going to be larger or smaller than W? And that's going to tell us if we make it or not. Okay, so take the values that I have here and plug it into the equation that I have in part D. That's going to say that the distance D is going to be 10 meters per second times the square root of 2 times 2 meters times the acceleration due to gravity. This is 10 meters per second squared. Okay, so this is going to be 10 meters per second times the square root of 40 meters per second squared. We're trying to be very exact here, so I can't really approximate this, but were I to approximate this, this is about 36 is 6 squared, 6 squared, 7 squared is about 7 squared is about 49. So it's somewhere in between 7 and 6, but I'm going to actually use a calculator here so I can get an exact value. So this is going to be the square root of 40, which, like I said, it's going to be somewhere in the middle there. So this is 6.3. So this is going to be, ultimately, this is going to be 6.3. Something's wrong. Something's very wrong, actually. Something's very, very wrong. Here's our dimensional analysis. So this was not correct. I should have done my dimensional analysis before. This is going to be 2h divided by g. So I should have done my dimensional analysis. I went too quickly. But I'm catching it now. I'm catching it now because I'm looking at these units. And this should be meters squared. I lost a meter right here. But this is meters squared per second squared. That's going to give me, when I take the square root, meters per second times meters per second. That's not a distance. So something was wrong here, and it's because of that. Okay, so this should be more along the lines of, see, I didn't even need to put the numbers in here to know that things weren't going to be right when I did this calculation if I had checked my dimensional analysis before. Do as I say, not as I do. Okay. But ultimately, I did use tools. I checked it. So, okay. So this is going to be 4 over 10. I'm going to, I'm actually going to take the square root of this. So this is going to be 10 to the 1/2 times 2, ultimately. So the distance that you're going to go when you fall this height here is going to be 2 times 10 to the 0.5, or this is going to be 6.32 meters. Okay, now let's compare d to w. D is less than w, which says that for this velocity, Gravedigger's not going to make it. So we want to now, in the next part, I want to say how far short does it come? Okay, well, I could subtract those to find exactly how short. How fast would he need to go to make it? How fast would he need to go to make it? Then what you could do is you can say that W is going to be equal to V0 root 2 H over G. Solve for V0. V0 is going to be equal to W root G over 2H. This is going to be equal to 7.5 meters times the square root of 10 meters per second squared divided by 2 times h, which is 4. So we're going to get a 7.5 over 2 times root 10. So make sure we put our units in here. Make sure everything works out the way that it should. I lost there was a meter here. That meter cancels that one. So that's why that's second squared. And then this is going to give us units of velocity. Dimensional analysis, important tool. Make sure you use it. So this is going to be, it's the same thing as 15 over 4. This type of square root is not something that I can do in my head. If I was to approximate it, I would say it was the square root of 9, which is 3. But we want exact values here. So this is 7.5 divided by 2 times 10 to the 0.5. This is going to give us 11.85 meters per second. Okay, and that's what our velocity needs to be in order for him to make it. Okay, the last part, and I'm not going to do this explicitly, but I'll talk about it. So, say if Gravedigger has a maximum speed of 15 meters per second, how could you choose H and W to have an impressive show where it barely makes it? Choose combinations of H and W and pick the ones that you find most interesting. Okay, so for this one, really, all we're doing is we're looking at this equation that we have right here. We have W is equal to V0 root 2h over g. And then we're saying, OK, we say that V0 is 15 meters per second. Let's pick an h. So what's an interesting h to fall? Let's say 5 meters. 5 meters is about 15 feet. Okay, so we could say 15 meters per second times the square root of 2 times 5 meters divided by 10 meters per second squared. And hey, this one actually worked out really nicely. So this ultimately ends up saying that the width you could jump would be 15 meters. Okay. And so the whole idea here was to get you to think about these functions in such a way that they, how long have I been frozen here? To think about these in such a way that you can, you're thinking more in terms of the symbols and the fact that those symbols can stand for whatever you want, but you can make them real by putting numbers into them. I've always had problems with my cam link when I'm doing this with this computer, but hopefully I catch that sooner next time, so you're not just staring at me like blindly staring off into nowhere. Okay, so that's this question. Now the last part was, it's a little bit of a challenge, but something I talk about a little bit, I won't get so much into it, is that you guys are kind of in the point in your life where you're trying to figure out what it is you want to do with your life. And for now, you guys have decided you want to be engineers. It's a very good profession. But you might find that you don't really like doing the things that engineers actually do. And if you read this part H, and this sounds like something you really wouldn't want to do, certain types of engineering are not going to be for you. You might find that you like doing design better, you like doing computer-aided drafting, you do coding, or maybe the management side of it. But this is the type of analysis that you would do as an engineer if what you're doing is you're saying, okay, how can I model a system analytically and then make that model as accurate as possible? That's really what H is. I'm not going to talk too much about it, but think about that, because if you're trying to figure out what in engineering you want to do, or maybe you might find that you don't like anything in engineering, that's okay. But you have to be thinking about what are the things that I'm going to be doing on a daily basis as an engineer, and if some of them are things you don't like, or all of them are things you don't like, you should probably look for something else that you might enjoy better. Okay, so the next problem is going to be our monkey in the tree. So this problem, the way that I posed it in this way for a reason. I gave you all the numbers to start with, and the reason why I did this was because ultimately this problem is much easier if you do it all symbolically. It's a little bit of a trap to convince you that working symbolically is a lot better than working with numbers. I'll show you why. So for our monkey problem and the tree, I'm going to write everything in terms of vectors. So really the only vectors that I'm going to need are the position vector for the banana and the position vector for the monkey. But as always, what's very important when you're doing this is you need to define a coordinate system. Okay, I don't know that I like that blue. Let's do this a different color so that it stands out from the banana. Okay, so I'm defining my coordinate system here to be where the banana starts. And so I'm going to have some position equation, r sub banana, as a function of time, which is going to be equal to, now I'm going to do this quickly, but it goes all the way through this whole process that we did here. I'm just jumping straight to the vector. Okay. Now, if you do it like I'm doing it right now, make sure you understand why I'm writing all of the terms that I am, because jumping around like this is how you can make mistakes if you're not careful. So for our banana, there is some x portion, there's some y portion. The x portion for the banana is only going to have to do with the velocity that it has initially. This says that this is going to be v0 times t times sine of theta, okay, where v0 is the initial velocity that it has, theta is the angle between the horizontal and that velocity vector. And then in y, this is going to be plus minus 1/2 gt squared plus v0t times sine of theta, okay? So that's what we have for a banana. Now let's look at what we have for our monkey. So for our monkey, the position vector as a function of time is going to be given by, it has some initial position away from the coordinate system that I have drawn here in x. I'm going to call this a distance of d, okay? So what I'm doing is I'm defining this distance here to be d, okay? So that's, where is my monkey horizontally? And that's actually always the same, right? Because he's just falling vertically down, but he's offset from where we're defining the origin. So that's always just the distance d. Plus, now our monkey starts in the tree. That distance in y, I'm going to call h. So this is a height of h. So this is going to be h, no initial velocity, so that's that portion 0, minus 1/2 gt squared times y hat. Okay. Now, when we want to consider the condition for the banana getting to the monkey, this is to say that r sub b of t is equal to t catch. So the time it takes for the monkey to catch the banana from when it's thrown is going to be equal to r sub m of t is equal to t catch. Okay? And from this, we're getting two equations. Those two equations are going to look like this. So we're going to have d. So this one's coming from our x equations, right? So here are our x equations. D, so x equations come over here. D is equal to v0 t catch times sine of theta. Now for our y equation. So our y equations are going to come into play as well, right? So this is going to say that h minus 1/2 gt squared is equal to minus 1/2 gt squared plus v0 times t catch times cosine of theta. Oop, I made a mistake here again. So when I look here, this term right here is not a sine. This is a cosine. Okay. So again, I'm catching these mistakes that I'm making. I'm not doing this on purpose, by the way. I'm not doing this to try to prove a point. I'm just finding these as I'm going because I'm looking back line to line to make sure that everything is matching. So this one right here is a cosine. That one's a cosine of theta. Okay. So now this is v0 t catch times sine of theta. Okay. So when we look at this, well, the second equation, I have the same thing on the left as I do on the right. This is just going to be the same. I can cancel them. Now, let's form a ratio of these two things. And the reason why I'm doing that, ultimately it's two equations, two unknowns. We don't know the angle, and we don't know time, right? Nowhere in the problem do I say it takes a second or 2 seconds for the monkey to catch it, and we're trying to find the angle. So ultimately, I need to get rid of time from the equation. And you could algebraically solve one of these equations for time, plug it into the other one. But when you set it up this way, you see something special kind of happens here. So this is going, let me rewrite the equations. H is going to be equal to v0 t catch times sine of theta. D is going to be equal to v0 t catch divided by cosine of theta. I'm going to take the top equation and divide it by the bottom equation. When I do that, I see that h over d is going to be equal to, now here's the really interesting part. The velocity does not matter. It does not matter what velocity we throw this banana at. It will catch, it will get to the monkey, provided that you're throwing it hard enough to cover the horizontal distance. So there's a minimum. But provided that you reach that minimum, their velocities cancel, times cancel, and what we're left with is sine over cosine, which is tangent of theta. So ultimately what this says is that as long as this angle is such that I'm just pointing straight at the monkey, then you'll hit the monkey every time, provided you throw the banana hard enough. And I'm back to being frozen again. Sorry, this has probably been like this for a while. But that's actually going to be it for me. So you're going to see me go through this problem looking a little bit foolish as I'm doing it. But that's, I guess, just the way that's going to be. So take it easy, guys. I will post this along with the work that I have here onto Teams, and I'll also post another assignment right after this. Take it easy.